Okay, thank you for the introduction. I'm Ed Merks. I'm a subcontractor with Itemis that does tons of cool things. You'll see another speaker from Itemis later present some of the cool things they're doing there. Get rid of this build, sure. Okay, so I use this picture as I think of Java performance tuning as sort of a balancing act. You're constantly sort of battling between memory footprints and making things faster and the trade-off between those two types of things. Java performance is a complex topic. It's much more complex in the past with languages like C++, where you compiled to machine code and everything was predictable. The processors didn't have all this pipelining. So the performance used to be quite predictable. In Java, it's really quite a complex topic. A lot of people think Java must be slow because it's got this byte code that's interpreted, can't be as fast as machine code. But that's not true. With just-in-time compilers, you get machine-specific performance coming out of your Java code. But it is a complex topic. You have different platforms, different operating systems, different VM implementations, different versions of the language, and all of them behave differently, and what's optimal in one place might not be optimal in another. I mean, obviously for performance, making things fast is sort of the ultimate goal. But it is a trade-off, like I mentioned. You know, having a nice Ferrari is great on the German Autobahn where there's no speed limit, but when you're in Berlin and you want to park your car, there are other considerations. So sometimes footprint is more important than performance. And in the ideal world, you kind of get something that's super fast and you could park in any available parking spot. That would be ideal. In the end, you know nothing about your performance if you don't measure it. So all of this stuff comes down to measurements. No measurements, it's just a grab bag. One approach to measuring is this sort of approach of benchmarking, establish very well measured points of reference against which you can measure other things. Another approach is profiling, taking sort of an external view of the code and looking at it kind of like under a microscope and measuring it from the outside. Those are the sort of two approaches to measurements. I think this is one of the key messages I want you to take away from this is just be paranoid about this whole topic. Don't trust what people tell you. Just trust nothing. Even your own measurements are unreliable. And in particular, don't trust what your friends tell you because they're stupid and they do stupid things. They know nothing. Don't trust your measurements. They're unreliable. You'll get different results, different times of the day, and depending on the temperature of your machine and all kinds of variables that you don't even understand where these differences are coming from. Don't trust yourself. You're probably stupider than your friends. You know nothing about this performance thing. And really, it's quite shocking, but I think most Java developers couldn't tell you how expensive an object allocation is, how expensive a method call is. We build things, it's like building a building out of bricks and really not knowing what the load factor on the bricks is. It's just kind of a bizarre situation. Also, don't trust the experts. I'm here to tell you all kinds of stuff, but what I tell you is unreliable. You really need to measure things yourself and make sure you've convinced yourself. And in fact, don't even trust me. I'm probably the worst person to trust. And no, that isn't me on the left, the black one. So clearly this is not a person you can trust. So keep that in mind. And there's a reason for this. I think in general, anything you can do or say about performance is sort of transient and volatile. It's transient because whatever's true today is probably not going to be true tomorrow. Somebody's going to change the VM implementation, and all of the assumptions you make, suddenly something is 10 times faster that you were assuming is slow. Also, whatever you measure on your hardware is probably different on somebody else's hardware and different on somebody else's VM implementation. So even if you sort of strive for this absolute knowledge about performance, you have to accept that it's something that changes over time and that it changes in different contexts. So you have to ask yourself, where does that leave me? And really that's the approach a lot of people take. Just write sloppy code, it doesn't matter as long as it works. And if there's a problem, it's because Java's slow, the tools are bad, or whatever. You find someone to blame other than yourself when you have a big giant mess on your hands. But that's really not the message I want you to get out of this. There is no excuse for bad code. You have code that looks like this disaster area here. It's not going to perform. You're not going to be able to maintain it. So you need to focus on producing proper, well-designed code and understand the building blocks that you're building with so it also performs well in the end. So the number one thing, and this requires no measurement whatsoever, is the algorithmic complexity of the code that you're writing. This is generally the killer. If I go to a contract and I measure the performance of things, inevitably the biggest things that need attention is some bad algorithm somebody wrote, something that's n-cubed. So in general, it's nice if your algorithms perform in a way where the size of the input has no impact. So something like a hash map, it's arbitrarily big, but you can get objects in and out of them with constant time. It doesn't matter how big the map is. That's the kind of thing to strive for. Generally, you expect linear performance. So if your input gets twice as big, you expect everything to take twice as long. But we know from computing science that things like sorting are more complex than linear. You end up with n log n performance. Anything beyond that is probably not going to scale well. Will work fine for limited input sizes, but you really need to aim for this sort of linear or better or n log n performance in the worst case. In a recent contract I started, I look at sort of how they're updating the UI, and I see when you add a node to a tree, it refreshes the whole tree. So of course they're complaining when they have 1,000 nodes that it gets slower and slower and slower. This is not going to scale. You'd hope that modifying a structure will cost in proportion to the number of modification and not in proportion to the size of the overall structure. This is also the number one thing that I see, and it drives me completely crazy, is don't call the same methods over and over again. And in a situation like here, you can see the argument that's coming in, we're calling getName on it every single time in the loop. So that's completely inappropriate. You don't need to measure to see if this is a bad idea. That's a constant. It doesn't change throughout the loop. So you want to take an approach, and there's nice tools in Eclipse. You can use Alt-Shift-Up arrow, it'll select the expression, and Alt-Shift-L, it'll assign it to a variable. These problems are very quickly solved by the tools. So this is what I would expect to see in the code. Get the name once, then iterate over the whole thing and compare the name against that. An interesting thing to note about Java 5 is that there's lots of things hidden inside of this loop. There's actually a creation of an iterator. There's a test that has next, calls to next. And as the objects come out, you need to cast them. So it's nice that we have these very simple notations in Java, but they do have a performance penalty as well. And we'll look in details at some measurements, what those overheads are. Another thing that's interesting in Java 5, when you override a method that's generic in the base class, so here we have a specific override for string, that Java generates a bridge method. So the code that callers of a hash map will call the object method, and then there has to be a cast, and then it calls this bridge method, and that has significant overhead. So it's often better to do this kind of stuff at the generic level rather than at a type-specific level. But here we're an example, we're just interning the string as we're putting it into a map, and we really do need to do the casting. But that has overhead. Another interesting one is accessing private fields. Here we make a simple data structure and we get the sense we're just doing direct memory access here. But in Java, it will generate bridge methods for this as well, and every use of X actually is a method call and is much more expensive than accessing a field. So in a simple context like this, we'd be better making those fields protected because the overall class is private anyway, so no one sees it. So I mentioned before, one of the ways of doing your measurements is profiling. I don't want to talk too much about profiling because all the tools are pretty much proprietary and cost money. They take two different approaches. One is this tracing approach, where the bytecode itself has hooks instrumented into them. So every entry and exit from a method is carefully instrumented. You know how many method calls there are, the interval of time in that method. Gives you very detailed measurements, but it's extremely invasive. There's a lot of overhead to record those calls, so things will run like 10 or 20 times slower, and something that you measure that takes 5 minutes will take 45 minutes. So it's very disruptive. But in general, although things run slower, the proportional amount of time spent in each method is still reflective of what it does without the profiling overhead. An alternative approach is sampling, where at periodic intervals it just looks at the state of the stacks of all of the threads, and that gives you more of a statistical sampling type of view of, you know, if I look at this process running 1,000,000 times, what methods is it in the most often? So that's good for finding hotspots. So in general, to improve performance, call it less often. It's just shocking when I look at code how people assume giant expressions can just be copied around in the code and that has no impact. Get rid of those things. So if I have lots of time, then I show a demo of the YourKit stuff, but I've never actually had lots of time, so I will not do that. I'll focus instead on this sort of benchmarking internal measurement process. So there's sort of two approaches we can use, sort of the older current time in millis or the nanosecond time, which has 1,000 times better precision. But the problem is both of these clocks are inaccurate. They generally are not useful for measuring things that take less than 2 milliseconds. So you'd think nanosecond time will give you very accurate time, but on many OSs, that clock does not increment at the nanosecond level, and it will not give you nanosecond accuracy, only this illusion of precision. So another problem with measuring, you can't trust the clocks to be very accurate. Other problems with sort of these micro benchmarks is the code in isolation will get JITted, just-in-time compiled, very differently from code in a bigger context. The number of subclasses has an impact. So it's often you'll measure something, but in a real context it'll behave somewhat differently. And that's even true for hardware. The pipelining processors, depending on what other threads are running and what sort of machine instructions are coming through the pipeline, can have a big impact on performance. And in the end, anything to do with threading, you can't reliably reproduce the threading behavior in a real application. So that's hard to measure. Another thing to keep in mind is the JIT's very smart, and it will notice that the code you're executing has no impact whatsoever, and it will turn it into a no-op. And that code that you think is running magically in no time is just not running at all. So benchmarks really need to compute something that flows out of the benchmark so that the runtime knows there's a reason to call those methods. Also, because of the inaccuracies in the clock, you need to generally do things for a long time to get macroscopic measurements. So benchmarks will generally do a bunch of stuff in a loop to end up with a macroscopic overhead. When writing a benchmark, try to do as much of the things you don't want to measure outside of the benchmark, all the initialization and setup. You'd also like to avoid measuring the cost of actually calling the benchmark methods, but rather measuring what the method does. There's this sort of notion of warm-up time. The JIT is quite smart. It doesn't want to spend its effort on code that doesn't get used very much. So often a method will not get compiled until it's called 10,000 times. So your benchmarks can run, and then at some point you notice they just suddenly start to get faster, and that's the reason. There's nice trace options you can add to the VM, so you can see when the just-in-time compiler is kicking in and get a sense when things are really warmed up. And of course you have to be careful of the garbage collector. A lot of time can be spent pawing through memory structures to see what's collectible, and if you have very large structures that are not getting freed up, a good fraction of the time is spent in the garbage collector. So I wrote this small benchmark harness that's in Git that you can add your own benchmarks to and verify that the things I say are true or not. It will run the thing that you've benchmarked a bunch of times to figure out how long do I have to run the benchmark, so it takes overall a second of time, so that these millisecond inaccuracies in the clock are not reflected in your final measurements. This is the hardware that I wrote on. Again, your hardware will perform differently for sure. So this is sort of the simplest thing that you can measure. Really what I'm trying to measure is how much time does it take to increment some field in a class. But you see, I have to do it a whole bunch of times in a loop so that I'm not measuring how expensive it is to call my overall benchmark class. So if I run this through the benchmark system, I end up with this statistical result. There is some variation from run to run, but in general it takes about 1/3 of a nanosecond to do this entire loop. And that includes sort of the loop testing, the loop incrementing, and the incrementing of a field, or computing a total. So this gives you a good sense of what the lower limit on sort of the fastest thing you can expect your VM to do. Things sort of at a fraction of a nanosecond. So you could do this 3 billion times in a second. So you can get quite a lot accomplished. I'd heard this theory that accessing a field of a class is more expensive than having something in the stack itself. So I tried to measure that, and indeed I find it's 10% faster. But then I put the two benchmarks together, and I find whichever one I run first is the one that runs faster. So those two different things actually perform the same, and for some reason the first one, I don't know, gets more attention from the JIT, but runs faster. There's no good explaining that. And again, that's the reason for this: be paranoid and don't trust anything. So if we look at sort of the next level of complexity, how expensive is it to do this array accessing? I run this benchmark, and it's actually faster than adding I. So instead of saying total plus equals I, I'm indexing the array. It's actually faster. Again, why? I don't know. You'd really have to look at bytecode and understand that. But this kind of conclusion, it takes negative time to access an array, is clearly nonsense. So you have to be very careful what conclusions you draw from your measurement. So I take a different approach, and I make sure I do exactly what I did before and only do some additional stuff. So I'm still doing the plus I and the array, and then I do a measurement, and now I can get a more sensible conclusion that it takes 0.15 nanoseconds to index into an array. So arrays are very efficient data structures, extremely efficient. And we can take the same type of approach and say, well, let's assign that overall result to an array so we can see how expensive it is to stick data back into an array. And by doing the differences between the benchmarks, we can conclude that it takes 0.3 nanoseconds to assign into an array. So they're all sort of reasonable numbers, and you'd see these are very fast, low-level operations. Now we look at something that takes a little bit more time. So we do the same type of loop. It's an array of strings, and we call the hash code method on it. And doing the analysis of the differences, we can conclude it takes almost 5 nanoseconds to call the hash code on a string. So you see, that's an order of magnitude longer than these sort of basic increments and array access. It's relatively expensive to call a method as opposed to doing these low-level numeric types of things. And we can see how long it takes to call a native method. Here I do the same thing but with an object instead of a string, and I know that's a native method. And we can see that's significantly faster to call that method. But the interesting thing about method calls is sometimes they can get in line. So I can look at some of those kinds of differences. So here we do the same types of thing with a list. So rather than using arrays, it's very common to use collection classes types of things. So here I'm indexing over an array list and calling get, but doing what we were doing with the array. And if we look at the performance of this, we can conclude it takes 1/3 of a nanosecond to call get on a list. But that's the order of magnitude slower than we've already concluded a method call is. So from this we can conclude that that method call is being inline, that this is as performant as using an array and accessing the array directly. Very little overhead in using the list. So that's sort of our conclusion here, is that with the inlining, many things get inlined, and ensuring that structures are well designed so that inlining is possible is one of the keys to getting good performance out of higher level APIs. But it's hard to know when those things will kick in. And it's doing these kind of benchmark measurements to verify that inlining is actually working is very useful. So most of this, whether things get inline or not, comes down to finality, whether the methods that you're calling are known to be final, whether it knows exactly which method it's dispatching to so it can act like a macro and put that code in line. I mentioned this earlier, a lot of times this doesn't kick in until a method is used 10,000 times and exits properly, and then the whole implementation can be replaced with something faster. Another interesting thing to realize is that as you load new classes, there can be subclasses of existing classes. Sometimes the JIT really has to undo its effort to inline and redo them based on new implementation assumptions. So in EMF we have something called a basic EList, so I wanted to compare that just to an array list. And you can see that it performs only slightly slower than an array list. So EMF has some very well-tuned, efficient data structures under the covers. And one of the things I wanted to do is try to measure casting. So here in this approach you can see I've got an array of strings, so no casting is involved. So I can contrast that measurements with the list implementation, where I know it has to get an object out and cast it to a string. And from this I see casting is almost free. It's incredibly cheap. And I know from 10 years ago, casting was shockingly expensive. So that's something that's changed dramatically since I started working on EMF. If we look at another example of a method call, here we're calling getName on a named element, one of EMF's sort of underlying meta models. We can see that this method call takes very long. This is taking 3 times longer than the other method calls that we've been looking at. So method call overhead can be very different depending on whether you're calling methods on a class or an interface and how many subclasses of that interface there are. So I can do some more analysis of these numbers to see how expensive casting is. But again, the overhead is something that I've not been able to measure properly. So I get some very good numbers, but then my machine, I can hear the fan comes on and then my benchmarks start to run slower. It's quite bizarre behavior. So in the end, casting is quite hard to measure. It is way faster on modern JVMs than it was 10 years ago. It has a cost. I've really not been able to pin down accurately what that cost is. So we can look at some data structure access, getting again back into the algorithmic complexity issue. We can do a contains test on a list, and this list has 1,000 items in it, and you can see what a humongous number we come up with. So this having to iterate through the whole array list to see is the object there is super expensive. EMF has something called a fast compare. It's basically an array list that uses equals instead of dot equals. And you look at the performance and you see it runs 10 times faster because it doesn't have to call equals on these objects 1,000 times. So a dramatic improvement if that's appropriate for your data structure. We also have something called containment EList. You see I'm doing exactly the same measurements here, but this takes 5 nanoseconds to do instead, which seems impossible, but in fact, doing a contains test on a containment list is constant time. An object knows whether it's in that list or not. It does not have to look at all the objects in the list. So it's this kind of thing that makes EMF's data structures perform well. When you build an entire tree, we need to add objects everywhere, and they need to make sure they're uniquely added. So if we didn't have this type of optimizations, building a tree would become an n-squared operation rather than a linear operation. So again, this algorithmic complexity thing is key, and looking at these types of numbers at a low level are key when you're building a framework that needs to perform well. I'll quickly go through another few data structures. I'm running out of time and I'm interfering with people's coffee, so I will move along quickly. If we look at something like a hash set and we look at the contains test on that, we see that performs extremely well, much like the contains test on a containment list. So things like hash structures are designed to be constant time performance. You need to aim to use those as much as possible. If we do the same type of tests but put a synchronized list in there, we can see it's very expensive to synchronize on methods. It's several times more expensive than a hash map lookup. So adding the synchronized keywords to your data structures will definitely slow them down significantly. So be careful with synchronize. It is expensive. And that's why we have new things like string builder instead of string buffer, because they avoid this overhead when it's not necessary. Object allocation 2 is quite shockingly expensive. You can see how expensive it is to allocate an individual object, sort of an order of magnitude more expensive than a hash map lookup. So again, it's often the case if you can reuse data structures instead of allocating them and letting them be garbage collected, there's a lot of potential for performance improvement. A quick sort of look at loops, the overhead in loops. You can see when you run this particular loop that the overhead of about 1 nanosecond, and in this case the loop is always empty, so really all I'm doing is calling size and noticing that the thing is empty, that takes about 1 nanosecond of time to sort of iterate over a loop and find out that it's empty. If we do the same type of thing with a for each loop, which is much nicer coding style, you can see the overhead is much higher. Here we're creating an iterator, we're calling has next, and then we're noticing the list is empty. So this is quite often a common pattern I see performance problem, is that you're looking through data structures that are mostly empty and you have a lot of overhead from this iterator creation and iterator testing. Although interesting to realize that this has to allocate in an iterator, but it's not taking the 40 nanoseconds that it takes to allocate an object, because the allocator is quite smart that it knows objects that don't escape the scope and it doesn't put them on the heap and have as much overhead as a general heap allocation. So if we do these same types of tests again, but do them with lists that actually have a few objects in them, do all the calculations, we can see the overhead of calling next on an iterator is about 1/3 of a nanosecond. So in general, if you're iterating over large structures and doing quite a bit of work, this loop overhead is irrelevant, but if you have a lot of almost empty structures, it's very significant. And a quick look at hash map. It's like you'd expect from the set contains. It has a, very low overhead to do a hash map lookup. It's interesting to compare that though with reflective access in EMF. And eGet is much like a hash map lookup, and in fact it's more type safe. It does all kinds of type checking. You can see it's actually faster than a hash map lookup. So again, this is one of the reasons EMF data structures perform well. If you compare that to Java reflection, you can see Java reflection is an order of magnitude sort of more expensive. Java reflection is still quite an expensive thing, so way cheaper than in the past. So one little anecdote here, I worked on a contract and 5% of the time was spent in this method of the overall several minute running application. And everyone concluded we need to put a map in there because it's iterating and finding the named thing is way too slow. We need a map. But in fact, when we looked at the get elements, this list we're iterating over, we saw it was allocating a list. And if I look carefully at the numbers, I saw that this get name and equals were not actually called very many times. So what was actually the case is most of the lists were empty and not allocated yet. So all of that code was allocating lists and then iterating over those and finding they're empty. So the simple change of accessing the field directly and using a counted loop made that thing, instead of taking 5% of the time, take 1% of the time. So this is kind of the exception to the rule, though. Generally, so the nice written code will perform well. The JIT will do a good job on that. But there are times when you need to look in detail at something and write something a little less nice to get it to perform well. So some key messages to take away from this talk. Focus on what's important. Algorithmic complexity is the most important thing. Focus on that first. Focus on writing nice code. It has to be readable. The JIT's very smart. It will take most of your readable code and make it perform extremely well. And don't make excuses. Oh, the JIT will inline that. It will, it might not. Don't repeat your code. Don't call the same method more than once and hope it performs as well as a direct memory access. That's a bad excuse. In the end, measure, and don't trust your measurements. Do them many different ways. Unfortunately, it's this Heisenberg uncertainty principle. You disturb the system by measuring it. You make it behave differently. It's a fact of life with this system. But in the end, without measurements, you know nothing. You have to accept there is a Heisenberg uncertainty principle involved. So focus on what's important. Use something like a profiler to tell you where to focus your efforts so you don't make things that are irrelevant fast. Because in the end, a lot of times what appear to be really big things don't matter at all because the code spends no time there. And other times, like the anecdote I just showed you, a little tiny thing makes a huge difference. So it's very important you spend your time productively focused on things that make a difference. So I use open source, I rob pictures from the internet, and they all require me to give credit for that. Okay, I'm 5 minutes over time, so maybe 1 or 2 questions, otherwise I'll answer them during the break, and then we can all get coffee, yay.